In today's lecture, we are going to talk about the different transport processes and their descriptions. Now, when we talk about transport processes, we not only mean heat transfer, momentum transfer or mass transfer, we also are going to talk about the mechanism of these transport processes. For example, in some situations, the convective transport process may become important, in some other cases conductive, and in some cases both would be important. So, when we talk about conductive transport process or molecular transport process, in which the transport is going to be proportional to the gradient of a quantity that can be measured. For example, it could be velocity for momentum transfer, temperature or concentration, and the corresponding phenomenological equations such as Newton's law of viscosity or Fourier's law of conduction or Fick's law of diffusion, they essentially define a transport coefficient, which could be the viscosity or the thermal conductivity or the diffusion coefficient. So, these are a cluster of transport processes in which the transport is due to the presence of a gradient in a direction perpendicular to the flow. So, if we have a difference in temperature and for example, in a solid, then the heat transport is going to be proportional to the temperature gradient, and the proportionality constant is the thermal conductivity of the fluid. So, there will be some situations in which the transport is primarily going to be governed by the molecules without those molecules actually displaced from their average positions. In some other cases, it is the bulk convection, bulk transport of material between points 1 and 2, and they will carry with them the corresponding momentum, energy or material transport from one point to the other. So, whenever we have transfer of material from one point to another and thereby causing some transport of mass, momentum or energy, that kind of processes are known as convective transport process. The convective transport processes are predominantly, they are the mode of transport in liquids, though in liquids the conduction is also present, and these type of coupled convection and conduction problems are quite important, and we are also going to look at the effects of convective and conductive transport in microsystems. So, we would see in this is the transport processes, their classifications and the properties, the coefficients which are important in some such processes, the governing equations for momentum transfer, heat transfer and mass transfer, and the relative importance of convection and conduction as specified by some engineering parameters and similarity parameters, and their relative importance, which would tell us that which process is going to take longer to establish a fully developed condition. And when mass, for example, mass and heat transfer are taking place simultaneously, then we would like to know which process is faster. Okay. For example, in the case of condensation from a vapor onto the surface of onto a cold surface, we would like to know whether it's governed by the thermal process or it's governed by the diffusion of the vapor molecules from the bulk to the cooler surface, and thereby creating an ideal condition for condensation. So, these differences we would also like to look at in today's class. Furthermore, we would also like to see what would be and just one applicative example is, for example, if we have flow, simultaneously flow and heat transfer in a slender microchannel, a microchannel which is thin yet long, and we would like to see what would be the governing equations for such cases and how additional forces could be incorporated into the governing equation. For example, how the surface forces can play a prominent role in such cases. And finally, we would also like to see the engineering application of these equations, for example, in terms of finding out what would be the pressure difference between points 1 and 2, and not in a straight pipe as we have already known from our undergraduate fluid mechanics, but in a system in which we have there would be large number of bends, there would be internals, and we are going to concentrate on smaller dimension pipes in which the length is going to be large compared to the cross section, and the cross section itself has many is following a tortuous path, so the pressure drop is going to be more. So we are going to start with the transport processes, and we would see how it changes. So since it's taking some time to load, then let's talk about the relevant equations in transport process and their descriptions. See, for example, all of us know that the governing process in fluid mechanics is if we go by elementary transport process and their descriptions, what we see here is the change of any variable is described by the transport process of conduction in the immobile phase, but essentially the governing equation can be written as total flow of any parameter. It could be energy, it could be mass, or it could be the momentum. Is if we define a control volume consisting of 6 phases, then through all these 6 phases there can be transport of momentum, for example, into the control volume, and there could also be convection due to flow of fluid into the control volume, and there could be some source or sink. So let's think of what happens in a system in which momentum transport is taking place. So as a result of all the momentum which are coming to the control volume, the density, the flow the momentum, total momentum contained in the control volume will change. And how would it change? There can be 6 phases. Through the 6 phases we can have conduction, molecular transport of momentum into the control volume, and they exist because of the gradient in velocity in a direction perpendicular to the flow. So I have a x phase and a x plus and another phase at x plus delta x. So the area of the x phase could be delta y times delta z. So x phase is the area which is perpendicular to the x direction. So I have another phase which is at x plus delta x. So if I have flow in this, then it's easy to find out what is the total amount of momentum being added by conduction into the control volume. So it would simply be the component velocity Vx in this direction multiplied by the area, which is delta y times delta z. So Vx times delta y delta z would give me the amount of fluid which is coming into this control volume per unit time. So multiply that with rho, and what I get is the amount of mass which is coming into this control volume per unit time. So this mass flow rate, when again multiplied by Vx one more time, would give me the x momentum, the x component of momentum which is entering the control volume. So the expression for momentum coming into the control volume would simply be equal to rho times Vx times del y del z and a Vx again, everything evaluated at x. Similarly, the momentum which is living through the x plus delta x phase would be all these quantities, but they are evaluated at x plus delta x. Similarly, for the y phase and for the z phase, one would be able to obtain what is the y component of momentum being added to the system and the z component of momentum being added to the system. Similarly, through all these phases, due to a difference in velocity, the momentum can enter, the x momentum can enter because of the presence of a gradient. Those are the conductive transport of momentum. So, through all these 6 phases, due to the presence of velocity gradient and applying Newton's law, I should be able to find out what are the expressions of tau xy, tau xz and tau xx. Similarly, for 3 y components and for 3 z components. So, together we then would be able to find out all the components of the stress tensor. So, sum this over the boundary for the conduction and for the convection, plus there would be source or sink. In these source or sink, it is simply going to be the forces which are present in the system. Now, for a momentum transport situation, the sources or sink that are relevant are due to surface forces, and the surface forces for macroscopic systems would simply be equal to the pressure forces and the shear forces. And when we talk about the body forces, it could be the gravity or the electrostatic forces or some other such forces which are applied on the entire volume, entire mass of the control volume. So, based on that, I can write the source or sink components of this equation. So, we know what are the conductive transport, the convective transport, and as a sum of all these, the total flow density or the total energy content or the total amount of species inside the control volume may be different, and this would give us a complete description of the flow physics in terms of either mass, heat or momentum. And the transfer coefficients are defined as the diffusivity d, the kinematic viscosity which is mu by rho, and a thermal diffusivity which is k by rho Cp, where k is the thermal conductivity, rho is the density and Cp is the heat capacity. All 3 transport coefficients, namely the diffusivity, the kinematic viscosity and the thermal diffusion coefficient have units of meter square per second. Now, if we look into the dynamic behavior of viscous fluids, we will see, I mean this I think we have covered before, a dimensionless number or a similarity parameter named the Reynolds number would appear in all the equations. And the dimensionless number Reynolds number is defined as a length scale, the velocity, the density divided by the viscosity. Now, the importance of similarity parameters are simply that if the similarity parameter of 2 different fluids under 2 different conditions are equal, then the process, be it heat transfer, mass transfer or momentum transfer, then the process can be described by governing equations which are identical. If we express the if we express the equations, governing equations in a non-dimensional form, then these similarity parameters, for example Reynolds number, would appear automatically. And the moment the process conditions, if the process conditions are such that for 2 different fluids the values of the Reynolds number are the same, then the governing equations describing the process would be equal. So, Reynolds number typically tells us about is important for viscous fluids, and it tells us, it's basically gives us some ratio of inertial forces and viscous forces. Similar to Reynolds number in fluid mechanics, we have convective flow, for example defined by Schmidt number in mass transfer, denoted by SC here, which is defined as mu by rho d, mu being the viscosity and d being the diffusion coefficient. So, if you look carefully, the Schmidt number is nothing but a ratio between momentum transfer and mass transfer, or specifically it is the species transfer. So, the values of these numbers would tell us something about which process is important. Is it the momentum transfer process that is more important compared to the mass transfer, or otherwise? So, if we can also say that if Schmidt number is of the order of 1, which happens for the case of gases, then the momentum transfer and the species transfer are in the same order of magnitude. So, let us say we have a flow of a gas through a pipe, through let us say a small slit, and that slit is made of a material which can sublimate. For example, it's a naphthalene slit, two plates of naphthalene which are kept close to each other, and we have flow. So, there is going to be the formation of a hydrodynamic boundary layer and the formation of a mass transfer boundary layer. Now, we do not know a priori which one is going to linger for longer. That means, we are not sure whether it's the mass transfer which is going to be the faster, or the momentum transfer which is going to be more which is going to take place at a higher rate. So, if we see the value of Schmidt number, which is mu by rho d. So, if the value of Schmidt number is, let us say, about 1, then the viscous transport of momentum and the species transport are of the same order of magnitude, and both these boundary layers will grow together, and the fully developed condition in terms of momentum transfer and in terms of mass transfer are going to attain at the same point or at very close to each other. That means, both these processes, momentum transfer and species transfer, will take place at the same rate. So, concentration profile and the velocity profile as they grow will be similar in nature. So, similarly, we can also see that if Schmidt number is large, now the value of Schmidt number being large, that means the value of the diffusion coefficient, which is in the denominator, would be small, and if the value of the diffusion coefficient is small, then it will take a longer path for the concentration gradient or for the concentration profile to become fully developed. That means, for large Schmidt number cases, such as for liquids, the concentration gradients will develop slowly compared to the velocity gradient. So, the velocity will be hydrodynamically fully developed, but not fully developed as far as the mass transport is concerned. So, these similarity parameters, the values of these similarity parameters tells us important information about not only the nature of the process, but how fast the different components of the processes are. So, the same conclusion that we can made about mass transfer and momentum transfer can also be made for momentum transfer and heat transfer. The corresponding similarity parameter of interest in that case would be Prandtl number, which is Cp mu by k, or in other words, it can be expressed as the momentum diffusivity by thermal diffusivity. So, if the value of Prandtl number is large, then the momentum diffusivity is going to be quite large compared to the thermal diffusivity, and same as in Schmidt number, the flow is going to be fully developed hydrodynamically, but the thermally it will still be developing. So, similar such cases, similar such analogies can be drawn between heat transfer and fluid flow, as well as between convective heat transfer cases, where both Reynolds and Prandtl number are going to be important, and where the Prandtl number is going to be of the order of 1, which would tell us that the process is as fast as in momentum transfer, but a different situation would arise when we are dealing with liquid metals. The liquid metals will behave completely differently in the case when we talk about the growth of these layers. For the case of liquid metals, let us see if we see for the liquid metals, the value of Prandtl number is going to be very small compared to 1. Okay. So, this would tell us that the thickness of the hydrodynamic boundary layer is going to be quite small compared to the thermal boundary layer. Now, if you see that Prandtl number is momentum diffusivity divided by thermal diffusivity. So, if the value of Prandtl number is quite small, then it only tells us the value of thermal diffusivity is quite large. Now, if the value of thermal diffusivity is large, then it simply tells us that the effect of the temperature of the plate, solid plate, which is in contact with a liquid, since Ts is different from the Tw, then the effect of the plate, hot plate, will be felt at a much greater depth compared to the effect of the plate when we talk about velocity. So, it will take this much of distance for the temperature to become equal to T infinity, whereas only this much of distance, this much of boundary layer thickness is necessary for the velocity over here to become equal to V infinity. So, we have a liquid which is approaching a solid plate whose temperature is different from that of T infinity, and due to no slip condition, the velocity at this point would be equal to 0. So, there is going to be simultaneous development of hydrodynamic boundary layer and thermal boundary layer. For the case of liquid metal, we can say that the delta T, that is the thickness of the thermal boundary layer, is going to be much greater than the thickness of the hydrodynamic boundary layer. So, this liquid metals therefore behave in a different way, but if these two are of the order of 1, momentum diffusivity by thermal diffusivity, then what you would see is that both the hydrodynamic boundary layer and the thermal boundary layer will probably be of the same thickness. That means, the boundary layer thicknesses at any axial position for these two cases would be almost equal if the value of Prandtl number is of the order of 1. So, the Prandtl number, Schmidt number, or similar such numbers, they carry information about the basic physics of the process, and not only they allow us to compare between seemingly different transport processes, their values will also give us such important information. So, this is a case of coupled momentum transfer and heat transfer. The processes are, there are also processes which are coupled heat and species transfer. Now, they are expressed in terms of Lewis number, which is nothing but the ratio of Schmidt number and Prandtl number, or alpha the thermal diffusivity divided by d the species diffusivity. So, obviously, we can say that if the value of Lewis number is large, then the diffusion, the species diffusion is going to be slower compared to heat transfer. On the other hand, if Lewis number is small, then the diffusion species transport is going to predominate over heat transport, which would give rise to some interesting phenomena which can be explained by high or low values of Lewis number. A high Lewis number allows droplet generation from vapor cooling, whereas for low Lewis number, the vapor will directly condense on the wall. So, the vapor will diffuse very fast, because if the value of Lewis number is small, Lewis number is nothing but alpha by d. So, if the value of Lewis number is small, then it simply tells us that d is going to be quite large compared to the thermal diffusivity. So, if I have a surface which is cold and if I have a vapor which is in contact with the cold surface, then due to its high diffusion coefficient, the vapor molecules will reach the cold surface before it feels the change in temperature. So, the vapor molecules will directly come in contact with the cold surface and condense and form a film on the wall. On the other hand, if d is quite small compared to the thermal diffusivity, then the effect of the cold wall temperature wise will be felt at a greater distance. So, the vapor which was coming towards this, it will sense the lower in temperature, thereby will start condensing, and droplets will be generated from the vapor, and these droplets will then come and condense on the cold surface. So, simply by looking at the values of Lewis number, by tuning the value of Lewis number, one can make the vapor come and condense on the cold surface, or if the value of Lewis number is large, then the droplets are going to form. So, all are connected with the relative values of the two diffusion coefficients, the species diffusion coefficient and the thermal diffusion parameter. Now, there are several models by which one can predict what would be the species transport, and there are this is just a case of a TwoFilm model, and the TwoFilm model can be expressed as like as I mentioned before. Then if let us say I am plotting the velocity profile, and velocity profile as so what you would see is that the velocity will sharply change, and it is going to become more or less parallel. So, this is the distance from the wall, and these are the velocities. So, you can see that there would be some arbitrary distance beyond which the velocity almost becomes invariant. Similarly, for the case of thermal temperature profile or species profile. So, this could be either the T as a function of y, or it could be concentration of one species as a function of y, whereas this is velocity in the x direction, main flow direction as a condition of y. So, there would be some portion, some point, some plane beyond which the temperature or the concentration does not vary. So, this is known as the hydrodynamic boundary layer thickness, and this could be the concentration boundary layer thickness or the thermal boundary layer thickness, and the relative magnitudes of delta H or delta T can be expressed in terms of the similarity parameters that we know. So, when we if we simply think of when we talk about the species transport equations and TwoFilm models, let us say this is the interface which separates these two liquids. So, for fluid A, and over here I have fluid B, and let us say I am talking about the temperature profile which is uniform in fluid A, but in a layer very close to the surface the temperature falls, and over here the temperature again decreases to ultimately it is going to become a constant. So, this will be the bulk temperature or bulk concentration of B and that of A, but over in this region near these two interface there would be two films on either side of the interface where the change in temperature or change in concentration takes place. So, one can therefore express, as we see over here, that the flux or the amount of transport of species 1 is going to be can be expressed as proportional to the distance of concentration of A in the ith fluid at the bulk minus at the interface, and similarly from the interface to the bth fluid. So, this way one can find out using a TwoFilm model the distribution of A or the transport of A across these interfaces. Now, when we have there are many equations, the many relations which have been postulated, derived from this two-film model. For absorption of gas into a liquid, we all know that Henry's law can be used, and for evaporation or condensation of a binary mixture, for example in distillation, the Raoult's law, that is also quite common. And these molecular velocities and macroscopic fluid properties can be obtained theoretically. For example, the properties can be obtained from kinetic theory, and I would request you to look at the textbook, the famous textbook of transport phenomena by Bird, Stewart and Lightfoot, which would give us, which will tell us about the values, the possible values of the viscosity, thermal conductivity based on molecular contributions, based on kinetic theory of gases, and there are certain relations which are available for viscosity of gases, the variation of viscosity of gases with temperature. From the corresponding equation, as you can see that mu increases with increase in temperature, and the dependence is root over T, whereas in liquids you can see that, we know that the viscosity decreases with increase in temperature, and similarly one can find relations based on kinetic theory from many of these textbooks for thermal conductivity and so on. But one important thing that we must keep in mind is that so far we are talking about, when we talk about Newton's law of viscosity, or let us say Fourier's law of conduction or similar such laws, that we expect a linear relationship between the force and the corresponding flux. So, when we are talking about the heat transfer, it's the amount of heat transfer is proportional to the gradient, or the amount of shear stress is going to be proportional to the velocity gradient, and this linear relation gives us the values of viscosity, the values of thermal conductivity or of diffusivity. So, till now we have assumed that there is a linear relationship between the cause and the effect, the temperature gradient and the amount of heat transfer, and the proportionality of this linear relation is the thermal conductivity. But these linear relationship will not be valid as the system dimensions are becoming smaller, or if the temperature gradients, for example, are too large. So, when you have a large value of gradient or the system dimensions becoming smaller, then the linear relationship will not be valid, and additional terms are to be added to those relations to make the equations more realistic, and to increase the applicability, region of applicability of these equations. So, as I was saying, when we talk about small structures, the linear coefficients are going to be limited, as the surfaces are going to play an increasingly important part, for example, in gases. In liquid, there is an interesting phenomenon which is known as the viscoelastic effects. So, the viscosity, or truly speaking, the liquid molecules behave differently in the vicinity of a surface, which is termed as the viscoelastic effects. Now, when we talk about flow of let us say a liquid in contact with a dielectric material, then the dielectric material, due to its electrical charge, will create an adsorbed layer of molecules from the liquid. So, that adsorbed layer of molecule will not move, and it is known as the Kelvin-Helmholtz electrokinetic double layer, or EDL in short. So, the presence of EDL, presence of an immobile layer of liquid very close to a dielectric material, creates a situation which is different from the bulk flow that we have been discussed so far. So, obviously, this very thin layer of thickness few molecules becomes relevant in describing the process if the system dimensions are smaller. So, few molecules adsorbed to the dielectric surface will not have any significant effect if we are talking about a conduit which is few centimeters in size. But when we reduce the size to 100 nanometer or even smaller of the conduit, of the tube or the capillary, then a few molecular thick layer adsorbed on the surface due to the and the formation of the electric double layer can cause significant changes to the flow properties. Not only the EDL, there would be additional changes because this layer, this EDL, extends approximately 3 molecular layers from the wall into the bulk fluid and induces a charge orientation in the adjacent fluid. So, this layer of liquid which is mobile but charged is called the Stern layer. So, since they are charged yet mobile, the movement or the velocity of these molecules would be different when compared to the situation in which the walls do not have any charge. So, this relatively, if we talk about very small channels and large molecules, then a few molecule thick layer of adsorbed layer on the surface and the presence of a Stern layer. So, that is why it is called double layer. The presence of an immobile layer and the presence of the Stern layer, their combined thickness could be significant compared to a 100 nanometer diameter channel. Now, what would this give rise to? This is going to create a situation in which, as if a more viscous liquid but uncharged, more viscous uncharged liquid is flowing through that 100 nanometer tube. So, these two situations are comparable. A dielectric with surface charges inducing an apparent increase in viscosity, that is known as the viscoelastic effect. So, as if the viscosity of the liquid certainly near the wall has increased, and this has given rise to less flow for the same value of delta p. So, there is a difference between the flow based on, depending on whether the tube is charged or it is neutral. So, the presence of charge induces an ordering or slows down the fluid close to the surface, additional slowing down of the fluid close to the surface, thereby it would appear as if the viscosity of the liquid has increased, the wall friction has increased. You require more delta p than that predicted by the ordinary equations which are to be used for bulk flow. So, this is another effect which one has to keep in mind, an effect of the transport property, how the transport, there can be additional changes in the transport property for systems which are very small in size. So, it not only changes the wall friction, since the velocity near the wall for such cases would be smaller, and therefore, the convection is going to be smaller, and if the convection is smaller, then the value of Nusselt number will turn out to be smaller as well. So, for micropolar flow, the Nusselt number could be about 10% smaller in laminar flow when there is no EDL. So, the EDL influences the flow, EDL and heat transfer for flow through very small systems. So, these properties of the transport parameters need to be looked into while thinking about flow through small systems. Now, when we talk about modeling we are going to talk about now about modeling, the calculation methods, and simulation. So, one can find out first what are the physical variables and try to do some dimensional analysis. Is there any similarity law that can be used, whether or not if there are any scaling laws. One can start with an order of magnitude analysis. We would also like to see if a lumped element modeling, that means assuming that, let us say for example, the temperature is space wise isothermal inside a solid which is in contact with the liquid. So, if we could say that the temperature is not a function of x, y, z inside a solid, then that simplifies our calculation to a great extent, and that is what is the lumped element or lumped capacitance modeling. There will be some situations in which these kind of approximations would be could not be made, and then we will probably have to go for full scale numerical simulation and or analytical modeling. So, we are if we think about once a single phase flow, then the relevant equations are obviously continuity equation and equation of motion and so on. So, the continuity equation, obviously we know that the substantial derivative that is capital D dt, substantial derivative of density is going to be a function of the del T of rho and the divergence of the mass flow vector. Similarly, for the case of equation and if it is a steady state, then we will simply know that the dot product of velocity times area would be the same, which would give rise to rho 1 V1 A1 should be equal to rho 2 V2 A2 and so on. For the case of equation of motion, what we have on the left hand side is the transient effect, which is del T of mw, and on the right hand side it is basically a sum of several factors. The first two are the amount of momentum, the net addition of momentum to the control volume as a result of convection as well as conduction. So, the first two terms represent the addition of momentum to the control volume. The next two that contain the pressure, they are the effect of surface forces, in this case identified as the pressure. The next term is the body force mg, and the last term is the additional forces which are acting or which are present in such in systems. So, using the correlations between the pressure and the shear stress, these are fundamental fluid mechanics, then and using Newton's law, one can write the equation of motion in the following compact vector form. So, for one dimensional, if we take just an one dimensional differential channel element with viscous flow, the momentum balance is simply a balance between momentum in, the change in pressure in the flow direction, the change in area in the flow direction, and the effect of pressure. So, the pressure between 2 points can be different, and not only that, the area at the 2 points could be different. So, if we have a curved area, and then we would also have to consider the component of pressure which is acting on the additional curved area, and then the next term corresponds to the shear stress. So, the shear stress opposing the flow, and the last term would be the gravity forces. So, for flow through a channel element, this kind of approach can be used to find out what is going to be the total amount of what is going to be the velocity distribution and so on. So, with incorporating the continuity equation, this equation can be simplified, and the compact expression for momentum transfer, as we all know, can be obtained. Okay. The second term on the left hand side is called the inertial term, and it describes convection, and the second term on the right hand side it denotes the viscous forces. The first term on the right hand side is the pressure forces, and the second term on the left hand side, or the inertial term, is the only nonlinear term in Navier-Stokes equation, and under certain special conditions this inertial term can be neglected and we get a simpler solution of the Navier-Stokes equation. So, there would be some situations, for example, when the flow is very slow. So, the convection will not have any bearing, any effect on momentum transfer. So, one can make a creeping flow assumption and get rid of all the convective terms on the left hand side, and therefore, it would then probably be possible to obtain an analytic solution for such situations. So, a creeping there would be several such approximations which can be made to simplify Navier-Stokes equation. On the other hand, when we talk about the energy equation for fluid dynamics, then we have to think about the mechanical energy equation and the thermal energy equation. So, combining these two, one get the total energy conservation, which is nothing but the sum of mechanical and thermal energy equations. And the last term phi on the right hand side is nothing but the dissipation, which is similar to fluid friction, similar to friction in solids. So, it can also be termed as the amount of dissipation that would result because of fluid friction, and this fluid friction increases entropy. So, in some cases phi, in some textbooks, phi is also referred to as the entropy generation. Okay. So, the larger the value of phi, the larger would be the pressure drop, the larger would be the temperature rise, the larger would be the frictional force opposing the flow in such systems. So, this entropy generation has to be kept to a minimum, and in order to build an efficient system. Now, as you can see, when we have a microchannel and we have several bends in the microchannel, there will be more dissipation and the more and more entropy will be generated. So, a design of a microchannel will also require a knowledge about how we can reduce this entropy generation, how we can keep this entropy generation to a minimum. And the boundary conditions that one use, these are no slip condition, no temperature jump at the wall, and so on. And if you are dealing with this, is already must be well known to you, that if we have a situation in which there is no viscosity, okay, it is a non-viscous flow, then Navier-Stokes equation can be simplified simplified by dropping the terms containing viscosity, and it is known as the Euler equation. But in microchannel flow, we may have additional forces, and this will have to be taken into account. So, we are going to I am going to give you a very quick example of modeling for flow in long and small microchannels. So, we have a slender microchannel with a rectangular cross section, and length in flow direction is much larger than the cross sectional dimensions. So, roughly the system would look like this, that I have a microchannel which is this would be the velocity profile, and this is flow in, and I have flow out from here, and this is the flow direction, and this is the diameter, hydraulic diameter of the channel, and this is the length of the microchannel. Now, when we say slender microchannel, we are going to assume that dH is much smaller than L. So, this is the system that we are going to model in using the equations that we already know. So, obviously, the continuity equation would be del V star in non-dimensional form, del Y star plus del W star by del Z star would be equal to 0. So, that is the continuity equation in dimensionless form, and the Navier-Stokes equation would be the pressure gradient plus the viscosity this is Reynolds number and the Z momentum equation. So, one can write the thermal energy equation for this case as well if the temperatures are different. The T refers to the T star refers to the dimensionless temperature. This is the Prandtl number, thermal conductivity, Prandtl number and Reynolds number squared. This EC refers to Eckert number and this is the dissipation function. So, these are the three equations which one has to find, one has to use, and this Eckert number is simply the flow rate square divided by Cp delta T. Now, in flow regimes where you have large Reynolds number, this term can then be neglected. Now, so in most of the macro flow problems, the values of Reynolds number are quite large and therefore, this entire term can be neglected. But in micro flows, the Reynolds number is generally of the order of 1 to 10. So, since in micro flows the Reynolds number are small, then this term cannot be neglected, and that creates additional problems. For solution of this thing. So, the full Navier-Stokes equation must be taken into consideration, and the effects of the velocities, the u, both u and v is not going to be negligible. Similarly, while dealing with the viscous dissipation, since the Reynolds number is small, the effect of this term cannot be neglected. So, one would expect that since the velocity is small, so the viscous dissipation, which is similar to liquid friction, would also be small. Okay. So, we should be able to neglect viscous dissipation for most of the cases of flow in microchannels, but that is not going to be the case because of the presence of Reynolds number square in the denominator. So, a small value of Reynolds number would lead to a large value of viscous dissipation even though the velocity is small. So, therefore, the important message is that viscous dissipation is important in microchannel flows, is extremely important in microchannel flows even though the velocity is going to be very small. Okay. And these three equations have been solved for different situations, for a different situation, and the solution which is there in some of the text, the solution is given over here, the last solution as a Fourier series, and one can look at this solution which is for stress function of a bar under torsion, and this would give the solution, this would give the velocity for laminar flow with a typical Reynolds with a small value of Reynolds number. Now, we all know that as Reynolds number increases, so this is just an example of how complex the situation could be in the case of microscale processes, since we have to solve the full form of the energy equation and the full form of the Navier-Stokes equation. Now, there are critical Reynolds number for internal flows which are available in most of the text is that for a circular pipe flow, when the Reynolds number is of the order of 2300, we get a change in flow regime. So, for plain Queth flow, the Reynolds number could be as small as 1800 when we get this change in phase, and in all cases the length scales are defined. For example, for the case of pipe flow, the length scale is the diameter. For the case of rectangular, it could be the hydraulic diameter. For plain channel flow, the length scale of relevance is the distance from the wall, and so on. So, the governing equations can be simplified for long channel geometries, and using continuity equation, Bernoulli's equation, and so on, and one would be able to obtain the total energy balance, the technical, incorporating the technical work that we all know that technical work is going to be positive for the case of if work is done on the system, for example in pumps and all, and if it is negative if it's produced work if it is done by the system, for example in turbines and so on. So, the viscous dissipation is incorporated in Bernoulli's equation as an additional term, as a head loss, and for the system of our interest, this equation has been provided in a book by titled Transport Phenomena in Microprocess Engineering by Kochman, and he has given that the pressure drop for a microchannel with a large number of fittings, vanes, valves and straight pipes, it's going to be a factor, two factors. One is due to the straight pipe and the other is due to the curved nature of the pipe, and the channel straight friction factor can be easily evaluated using Moody diagram, whereas the pressure loss coefficient has to be evaluated experimentally, and we all know that how to obtain the channel friction factor, and the other factors are the values of these friction factors are given in that textbook, the values of CF for different systems. For example, the value of CF as given for KOH trapezoid silicon. So, if you make a microchannel like this, then what would be the value of CF? This value of CF is given to be about 56, whereas we know that for a circle the value of CF is about 64. So, with the knowledge of CF as given in the textbook, one would be able to obtain what is the total pressure drop as per the equation for flow in a microchannel. So, that is all I wanted to cover today, and so this gives us a concise approach, concise description of the complexities associated with flow, heat transfer and mass transfer in microchannels, and we are going to continue with that in our subsequent classes. Thank you.